Okay, let's get the show on the road. So the last time we met, we talked about residuals and the residual plots. And we said that if I had a line like this, and this was the point, right, then the residual would be the difference here. This would be the residual, and we calculate the residual as the actual minus the predicted, right? The actual minus a predicted, and that's how you calculate the residual. So if it resides on top of the line, it is a positive residual. If it resides on the bottom down here, it would be a negative residual. Oh, we talked about that. We also talked about the residual plots. We found that we could do a residual plot in our calculator. And what are we looking for there? What are we looking for in a residual plot? If there is a distinct pattern, that means that we should not be using a linear regression, okay? We're looking for truly random, no pattern in the residual plot, because that, if you find that, that means that the linear regression that you are using is the proper one to use, okay? So that was the residual plots. Okay, so today we're going to start on page 188 where it says how well the line fits the data. How well the line fits the data.
Mr. On.
Yes.
Alia is trying to get in.
Alia is trying to get in.
Mm-hmm.
Oh. Okay. Well, she's here now. Okay. So we're going to talk about page 188.
Just a moment.
What? Okay, so 188, we're talking about how well the line fits the data. In other words, how good is my line of fit, right? How good is my line of fit? And we're going to talk about two things here. We're going to talk about this guy and this guy, okay? So we have the standard deviation of the residuals. This is the standard deviation of the residuals. And then we have the coefficient of the coefficient of determination, So this is the guy that when you turn on the diagnostic, when you had the diagnostics mode on, you had the R and the R squared, and you always kind of wonder what the R squared was. This is the R squared. It is the coefficient of determination, okay? So we have the standard deviation of the residuals and the coefficient of determination. Okay, so if you let's go ahead and look at the first one. Let's go and look at the standard deviation of the residuals. Okay, go to page 189. There's a green box there. The definition itself, it says, the standard deviation of the residuals S measures the size of a typical residual. Okay, that is, S measures the typical distance between the actual Y values and the predicted values. So we're going to go ahead and say this is the S's, right? These are the residuals here, and we're going to go ahead and measure those, and we're going to go ahead and find out what a typical residual is. Okay, how far away a typical point is away from the predicted value. Okay, so that is the standard deviation of the residual. So it's kind of the same as the definition of a standard deviation that we first thought when we first talked about. We said, okay, we have something look like this, and we had a standard deviation here, and we said that the definition of a standard deviation is typically how far away is a point away from the mean, okay? Same thing, standard deviation of the residuals is how far away is the residual typically compared to the predicted value, which is the value that's on the line of best fit, okay? So that is the standard deviation of the residuals, okay? And on page 89, there is a formula there that shows you how to do it, okay? So basically it takes the squares and then divides it by the number of dots minus 2, and then you take the square root of that, okay? So it's kind of like the standard deviation, okay, the way it's calculated. You do not know how, you don't need to know how this is derived. It's more important that you understand what it means, okay? Second one, coefficient of determination. Okay, this guy is the one that is pretty confusing, okay? It's pretty confusing. So let's go ahead and before we read the definition, let's go ahead and read the definition, okay? Because if you read the definition, it says the coefficient of determination R squared measures the percent reduction in the sum of square residuals when using the least square regression line to make predictions, rather than the mean value of y. In other words, R squared measures the percent of variability in the response variable that is accounted for by the least square regression line. So pretty simple, right? Everybody got that? Are we good? Okay. Nobody probably understood that. I mean, it's kind of hard to understand. It's really convoluted, okay? So let's go over this, okay? So let's say that I had all these points here, okay? I had all these points, and instead of using a line of fit, best fit, okay, if I'm not gonna use a line of best fit, what am I gonna use? I basically have a number of, let's go back to the F-150. This is the F-150 trucks, right? So I have a bunch of trucks values here, okay? These are all values. The response variable was the value, the number of how much money it was worth after the explanatory was miles driven, if we remember correctly, because this is the miles driven, right? So I have a bunch of trucks. I know what their values are, and if I don't use this, what am I gonna use? What else do I have? The only thing that I really have is the mean value. In other words, I'm gonna add all these together and then go ahead and regardless of the miles driven, I'm gonna say that's the average used value. And I'm gonna use that value. So it's gonna be a straight line across, right? Because regardless of the miles driven, it's going to be the same, right? And I'm going to use this as all predictive, whatever miles driven. I'm going to use that as to say that's what it's going to be used. That's going to be what the truck is worth, okay? Which is not a scientific way to go by doing it, right? Okay. So if I use this, now I'm going to have new residuals, right? I'm going to have a residual looks like this, this, this. And it'll be from here, and so here, it's about the same here, from here to here, here to here, here to here, here to here, here, and I was up here, so it's gonna go down to here. Okay, so I'm gonna have different squares. Now I'm gonna go ahead and now take these residuals, and I'm gonna do just like I did before, I'm gonna square them. I'm gonna have, so each one of them, I'm gonna square them. I'm gonna make a square, okay? That looks like this. I'm gonna add all those areas of the squares, right? And then I'm gonna compare that to the squares that I have when I use a line of best fit, okay? Obviously, the squares are gonna become smaller when I use a regression line, right? Because I'm going to have less, the residuals are going to be less, right? Because I'm going to be closer to the points rather than just a flat out average value, okay? So if you go back again to the definition, it says the coefficient of determination R squared measures the percent reduction in the sum of the squared residuals when you're using the least square regression line to make predictions rather than the mean value of y. Does that kind of make sense now? So when I go from the average, just using the average value, I'm going to have a large squared residual value. But when I use this, it's going to be reduced. And the percent, how much that gets reduced, is what is called the coefficient of determination. Okay, so the larger the coefficient of determination, okay, the larger the percent reduction I'm going to get. In other words, the line is going to be better. The line is going to be that much better because that much more of the squares gets reduced. Okay, the area of the squares gets reduced. Okay. It also says at the end of that definition, it says, in other words, R squared measures the percent of variability in the response variable that is accounted for by the least square regression line. Okay, right? So hopefully it makes sense. Right? If not, don't lose faith. You're gonna have to read it like maybe 4 or 5 more times and do some homework on it, and hopefully it'll get back to you. But again, it is the percent reduction of the squared values of the residuals that happens when you use the regression line versus just the average value. Okay, so let's go ahead and read the example on page 191. The scatter plot shows the hand span in centimeters and the number of Star Wars candies grabbed by each student in Mr. Tyneson's class, along with the regression line for the model. Interpret the value of S. Okay, the value of S is 4.03. Okay, again, S was what? S was the standard deviation of the residuals. So that means that a typical residual will be 4.03 away from the predicted value. Okay, that's what that means. And if you flip the page, it says that the actual number of Star Wars is typically about 4.03 away from the number predicted by the least square regression line. Okay, and then interpret the value of R squared. So this is a typical question in the AP test. They're going to say, interpret the value of R squared. Okay, so again, the way what you need to write is about 69.7% of the variability of the number of Star Wars candies grabbed is accounted for by the least squares regression line with the x is equal to hand span. Okay, again, so that is the second part of the definition that they're using there. Okay, okay, so interpreting the computer regression output. Okay, this is pretty simple. If you look at the page, there are 2 things going on here. There is the Minitab and there's the JMP. These are the 2 most prevalent statistics software that they use, or that we're going to use in this class anyway. So you have Minitab and you have what's called JUMP. You have Minitab and JUMP, and you have to be able to, given a Minitab output or a JUMP output, interpret what is what. Okay, that's basically what that is. Okay, so it says this. So let's look at the Minitab first. Look at the Minitab. On the very bottom line, it shows that S, okay, and it has an R squared value. Okay, so the S is basically the standard deviation of the residuals, and the R squared is the coefficient of determination. Okay, and it also shows the y-intercept where it says constant, and then it has the slope right underneath that. Okay, on the JUMP software, you have the same values, but they're in different places. Okay, in the JUMP, it has the R squared where it says R squared, which makes sense. Then it has the standard deviation where it says the root mean square error. Okay, the root means the RMSE. It's also sometimes called the RMSE, the root mean squared error. That is the standard deviation of the residuals. Okay, and then it has the y-intercept where it says intercept. And it has the miles driven there where it has a slope. Okay, so you have to be able to look, given a Minitab or a jump output, find out where these numbers reside in there, where these numbers are. Okay, obviously the R squared is going to be easy because it says R squared. And then you have to look at the constant and the miles driven for the Minitab to get the B naught and the B1. And those are in the bottom where it says intercept and miles driven on the other one for the jump. And you have to be able to find out where the standard deviation of the residuals are also. Okay. And we'll take a break here. We will go ahead and start working on our homework. So let's start working on our homework.